So we look at binomial distribution, which is the last in our discrete probability distribution. And we are not going to complete everything today, apparently, because we have to study the mean and variance of this distribution as well. Okay? We have only talked about mean and variance in general. Mean is expectation. Variance can be expressed in terms of expectation. That's for every probability distribution, discrete or continuous. And there are different probability distribution you will do later in the university. Probability distribution. If you go online, you will see different probability distribution that you will do. So under district, you can see on Wikipedia, district probability distribution. You can see here. Oh, I'm looking for some types, specific types. You see, Parsing, Bernoulli, binomial, geometric, and the likes. If you go to continuous, you will see normal, uniform, chi-square, and so on. These were the things I actually studied in my polytechnic days. And something called, I think it's statistical analysis. I can't remember the particular course. I really love that course. I wrote my polytechnic project on probability distribution. I can't remember which one that I chose, something exponential. I can't remember. Anyway, very fun stuff because it has calculus, so maybe that's why. Anyways, so under the discrete probability distribution, one is the Parsing distribution, which we didn't study directly, but it was a question in the book to prove that this is a valid distribution function. Do you remember that? We had to prove that the summation of the probability is equal to 1. We did that on Zoom. That is actually a probability distribution. It's called the Parsing probability distribution, but you don't need to worry about that. But for your syllabus, only normal was taken for district, only binomial was taken for district, and normal was taken for the continuous. Okay, why it is limited, I don't know, but that's what they want you to learn. How do you know the question is a probability distribution question? Once you notice the following. Number one, there is a fixed number of trials that you are looking at. So you are not talking about infinity. So, oh, this thing is done maybe 3 times, 5 times. Okay? Oh, I roll this die 5 times. Or 5 dice are rolled together. Rolling 5 dice together is the same as rolling 1 die 5 times. I flip these coins twice. I flip this coin 10 times. I flip this coin 100 times. And you are interested in probability of seeing the head or the tail. So there is fixed number of trials in that context. In the case of the Parsing distribution, you can remember that we always do summation from 1 to infinity, from 0 to infinity. Then you know that is not fixed. Does that make sense? There was, I don't know if we solved a problem relating to who eventually wins. Did you do any question on that?
Yeah.
Who eventually wins? Yeah. Did we do the question or I just gave you the question?
Homework.
Homework. Okay. So those questions are continual, that this thing is going to continue. Maybe during our revision period, if anyone has a problem with that, I'm happy to maybe solve 1 or 2. When they say eventually win, it means there's no fixed number. You continue over and over. So the question who eventually wins tells you, okay, this is not a fixed number. Then it can never be a binomial distribution problem. Understand? Also, there are 2 possible results in each trial. So in the case of flipping the coin, it can either be head or tail. If the problem is relating to die, you might think, oh, but die has 6. No. The question, that specific question, might be, what is the probability of that a perfect square appears? There are 2 possibilities. Is either a perfect square appears, or a perfect square does not appear. So when you have 1 and 4, that is the success of the experiment. When you have all the other numbers in the normal die, that is the failure of the experiment. Does that make sense? You are talking about, you see a question in the exam and it's talking about defect product. Oh, Karen has a company, they make light bulb, and they tell you the probability that the bulb will be, has defect. You know, sometimes you produce something in mass, there are some defect, right? Oh, 4% have defect from the factory. Okay, what is the probability that when we select from a random sample of 20, which means there are 20 trials, okay, what is the probability that, oh, maybe 5 of them will be defect, will have defect? So your random variable is focusing on what? The defect. Your probability of success is that whatever you pick has a problem. Then the failure will be it does not have a problem. So that is these two possible results. It means there is no other alternative. Do you understand that? It will be obvious in the question that there is no other alternative. So success is when the event occurs, failure is when it doesn't occur. I'll send you a screenshot of this, then you can maybe form a note later. I don't want to waste time writing this. Or maybe I can print for you, you stick in your note. Do you prefer that? Or you form your note later? Or do I type something, you stick in the notes?
Both of them is fine.
What?
Both of them is fine.
Okay, I will choose the one that I don't have to type if you don't choose. So you have to choose. If you want me to form a short note for you, and you can just say, or you can create it when I send you the screenshot. Choose one now. What?
Just a screenshot.
What is it?
Screenshot.
Screenshot. She's trying to be nice, like, okay, we don't want to give him too much work. Okay, thank you. So, now the probability is the same for each trial. This has to do with the independence. If we are talking about rolling 2 dice, if you roll the first one, it doesn't affect the outcome of the second one because you have to do it again. So in each case, the probability of getting a perfect square is the same each time you roll a die. You roll the die once, you get 2/6 for perfect square, right? You roll it the second time, does it reduce? No. You flip a coin, each time it's half-half. It doesn't affect. So each trial has the same probability, which means you are dealing with replacement problem. So if you are talking about, oh, a bag contains 5 red marble and 2 whatever marble, and certain marbles are picked, it has to be with replacement. Because if it is without replacement, your experiment will change the probability. It will change probability for the second trial and the third trial. In that case, you don't have a binomial situation. Am I making sense, please? So this is the summary of how to identify that the question you are dealing with in exam is binomial probability distribution. Understand? So let's move on. So I like this particular example. Brandy, please focus on the board. So now imagine that the random variable is the number of blues which returns when we spin this once. Of course, you can have either the blue is seen or the blue is not seen, isn't it? And if you are talking about the probability, here you'll be having, probability when the blue is seen. Is it 0 or 1? Definitely. This is random variable. Is it the blue is seen or blue is not seen? Or blue is not seen or blue is seen, isn't it? Again, the random variable is not talking about the probability that blue can be seen here. The random variable is the number of blues which results. And it will only stay flat on one side anyway. So is it that side is blue or it is not blue? So is it that the blue is either this number is a 0 or 1? Whether it is on this side, if it rests on this side, it is 1. If it rests on this side, it is still 1. If it rests on, there is no way two blue sides can rest together. Am I making sense? So that is why the random variable, the value that the random variable can take is just 0 and 1. When it is 0, it means you have white. That's 1/4. And when it is the other, you have 3. This is the probability distribution of this random variable, x, for this particular experiment. Okay? Now, suppose we spin this n times. When you spin it n times, does any of this change? So one of these is checked. Again, there are 2 possible results, blue or no blue. Okay? The probability is the same in each trial. That's also checked. The fact that it's n trial means there are fixed number of trials, and they are independent trials. What happens in the first spin does not affect what happens in the second spin. Am I making sense? Then you will see, now let's see So again, it says this is a binomial experiment if all those things are checked. Consider the above situation with 3 blue sectors and okay. Success is when the blue is seen, just like we have said. X is the random variable with N3. You see, this P is the probability of success. And can take the values 0, 1, 2, or 3. So this is when, how many is spin? 3 times. Spinning 3 times is the same as spinning 3 together. Okay? So it's like the extension of the first table. The first table is only when you spin it once. Am I making sense? You spin it 3 times, it's the same as you have 3 of the same thing, the same spinner, and you spin them all at once. That is why our random variable takes value up to 3. Because when you spin the first one, you can either have 0 or 1, isn't it? But when you have 2, you can have, if both of them are white, that's 0. It's possible you have 1, 1 from each, isn't it? The 1 and 0, 0 and 1. Do you think what I mean by 0 and 1? Okay, you have white, you can have white, blue. This is the first spin. You have white. The second one is white. In the second one, it could be white, blue, or blue, white. And the third spin could be blue, blue. So you can see here, blue is 0. Here, blue is 1 for these 2. And here, blue is 2. Okay? That's for 2. If you have 3 the same way, you can have white, white, blue, white. No, white, white, blue, white, blue. You understand? Then you have different combinations until you get to blue, blue, blue. So there are 8 different outcomes that we can list in our sample space. And when you count the number of blue, it will take either the value 0, 1, 2, 3. In this 8 sample space, or the space element in the sample space, there will be 8 elements in that sample space. Those 8 different outcomes will give you this random variable 0, 1, 2, 3 as their values. Am I making sense? I'm trying to explain something here quickly. Okay, so a tree diagram was used. Let's present this in a tree diagram. I like this tree diagram, which is very fancy. Very fancy. So, the first spin is either blue or white. Are you with me? Now, the fact that the first is blue doesn't mean the second is blue. You also have possibilities, because each trial is what? Independent. And the fact that the second is blue doesn't make the third blue, because each trial is independent. And so we have all this. And you can say that the probability does not affect as well. So clearly you will see that here you have all blues. The probability is this. Here you have combination of blue and white with 2 blue and 1 white. And I like how this color coding was done. Okay? And here you have 2 white, 1 blue, and this is all white. You will notice, can somebody put in the calculator, all of you put in the calculator, add the sum of these probabilities together. 3/4 cubed, 3/4 squared times 1/4. You see, this appears 3 times. So basically it is, you can put this 3/4 raised to power 3. 3/4 squared 1/4 appears 3 times. So multiply that by 3 instead of putting it separately. Understand? Then you can see 3/4 in one place, but 1/4 in 2 places. Also multiply that by 3. Then you have 1/4 raised to power 3. That's power 3 is power 2. What are you doing? This is plus completely. You're adding the probabilities. You need coffee. Computer needs coffee. Has anyone finished? What do you get?
Whoa, it's 1.
I think we can see that immediately. Can we see that immediately here?
Yeah, yeah.
How?
Because it is all
What is this? A cube. What is that? 3a squared b. 3ab squared b cubed. What is this?
That is. That's the. Oh yeah, we did this.
A plus b
Cube.
cube. And that is just 3 over 4 plus 1 over 4 cube. 1 cube. 1.
Oh, that's crazy.
Okay? So this is telling you the sum of all pi is equal to what? 1. Understand? Is it possible that these are not, that you can get an outcome different from all this?
Wait, what do you mean?
In this experiment, in this trial, can you get any outcome apart from this?
No.
No. So is it that this or this or this? That is why the sum of probability must be 1. Okay? So clearly, so when it says, oh, the probability of getting for x is equal to 0, which means the probability that no blue can be seen. Is that not? That will be this one, which means no blue means all green. All white. Is that not? And when it is probability that the blue that can appear is 1, exactly 1. Exactly 1 means you have 3 different places. Exactly 1 blue. Here, here, and here. And because of that independence, they are the same value. So all you have to do is what? Multiply by 3. This is the reason we use binomial theorem. Because you could see the form, the coefficient, the terms in your binomial expansion. That's why it is called binomial distribution, binomial probability distribution. The pattern gives you exactly what you have been seeing in your binomial expansion. So you will see this now, the summary. Notice that for any particular value of x, each outcome with this property, we have the same probability of occurring. The order of blue and white does not matter, of course. We know this already. Okay, this is what I've just explained, so no need to go over it. So this is it. It means for each value, like 0, 1, 2, 3, it is simply this. And since we have them, for the case of 1, we have them in 3 places. So there will be 3 of these. For the case of 2, we have them also, no. For the case of 0, oh no, it's already there. This is combination. This don't mix it up. When you have 0, this is just one of them. So 0 means 3 combinations 0. That's 1. So the first one is always 1. This one. Okay? When you have 1, you have 3. So the second one is multiplied by 3. When you have 2, you also have 3. And when you have 3, you have 1 again as the combination. This is 3 combination 0 is 1. And 3 combination 3 is also 1. Only the middle ones gives you 3. So this is like a summary of each of the probabilities. And this isn't that the term of each binomial expansion? Each term in binomial expansion. Okay? So quickly, so this is the final statement. This is what we really need. If x is a binomial random variable, which means a random variable whose probability distribution is a binomial probability distribution. Okay? With n independent trials, remember, the n has to be specific. It means it is, what was the word I used earlier? N has to be, I used the word earlier. Not independent only. The word that, why did I forget this? Somebody help me here. What? Fixed, thank you. Why did you go fixed? So the number of trial is fixed. Don't forget that. And the probability of success is P. If you are not used to this complex way of writing it, just use PQ. So P is the success, Q is the failure. And the relationship between P and Q is that P plus Q is equal to 1. Okay, let's see what I would love to use what our formula booklet looks like. so that you are used to it from classroom. Okay, they didn't put the probability formula. They just put the mean and variance of the binomial distribution. Okay, so you're on your own basically. Well, it's not a difficult thing. Just know that there are P and Q. I prefer this. This is how I learn. Probability that X is equal to X is simply n combination X, P raised to power X, Q raised to power n minus X. I prefer this. Where P plus Q is equal to 1. P is the probability of success. Okay? And Q is the probability of failure. Because writing 1 minus Q might look complicated to some of you. Of course, you are welcome to write that way. Understand? And so this is very important because of calculator function. If you have to use technology to write, to solve the problem, you don't just write the answer. At least show something like this. The probability distribution of X is called the binomial distribution, and we write like this. So if it is a problem that requires, when we get to the calculator format, at least you must write that, oh, X is a random variable which follows a probability distribution with n fixed trials and success of P. Okay, we will see how that is used. This is a very important notation that must be seen. We'll see how that is used in a bit. So let me play this quickly. The A part is not necessary, but maybe I skip that. It's just expansion. Okay, maybe we can hear one or two new information.
Part A of this example, we are given a binomial expansion. We know from earlier in the course that we can apply the binomial theorem to write it as a sum of terms. When we expand the sum, the power of 9/10 is 0 in the first term and increases by 1 each time. The power of 1/10 is 5 in the first term and decreases by 1 each time. The binomial coefficients are the fifth row of Pascal's triangle.
Remember that?
The reason for this binomial expansion becomes clear when we consider part B.
It is not
The
necessary,
archer fires
please.
5 arrows at the target, which is a fixed number of trials. For each arrow, the archer has a 90% chance of hitting a target, independently of all the other arrows.
Understand?
There are only 2 possible outcomes when an arrow is fired. A target is hit, or it is missed. We say this is a binomial experiment with 5 trials, each with a probability of success 9/10. The number of arrows X that hit the target is a binomial random variable. We can write a probability function for the distribution of a binomial
move it
random
up,
variable,
Nakita.
which is the number of successes
Thanks.
out of n independent trials, each with probability of success p. The variable is always an integer, and there can be anything from 0 to n successes. The binomial coefficient n choose x is present because it tells us how many ways we can order x successes and n minus x failures out of x trials. The rest of the formula is the probability of obtaining x successes and n minus x failures in a particular order. Notice that if p is the probability of a success, the 1 minus p is the probability of a failure. So, the formula is the number of possible outcomes with x successes times the probability for each of those outcomes times the probability for n minus x failures. This gives the total probability of obtaining x successes. In this particular example, the probability of success with each trial is 9/10, so the probability of failure is 1/10. The probability of obtaining x successes is therefore 5 choose x times 9/10 to the x
Frozen again.
times 1/10.
No, I think no, it's good, it's good.
Explaining using the
Oh,
You
okay,
should
okay.
notice how this expression is the general term of the binomial expansion in part A. So, the terms of the binomial expansion are, in order, the probability of 0 successes, which means 5 misses, the probability of 1 success and 4 misses, the probability of 2 successes and 3 misses, and so on.
Understand?
The probability that the archer hits the target exactly twice is the probability that x is 2. This is the third term of the binomial expansion, which is 0.0081. The probability that the archer hits the target at most 3 times is the probability that x is less than or equal to 3. To find this probability, we sum the probabilities for each individual value that is less than or equal to 3. This is the sum of the first 4 terms of the binomial expansion, which is approximately 0.0815.
It's frozen this time. So, but instead of that, you can tell me what else we can do for the last one. 1 minus x probability of x greater than or equal to or greater than? Greater than what? 3. Or greater than or equal to 4. So this is what you are adding, right? But you know that everything is 1. So it could just be 1 minus this. Imagine this is an expansion involving 10 terms. Again, you have done r plus 1 term of binomial. So there's no need to expand all this. I've not seen any IGCSE question that tells you expand 1 over 10 plus 9 over 10 raised to power 5. Sorry, IB question, no. But this is just the textbook building it from novice to guru. Understand? So you go to specific term that you need using your r plus 1 term or just general term of binomial. Okay? So that's basically it. Okay, I was going to say something. If this has maybe 20 trials and it's say probability of at most 18, that's from 0 to 18. It's not possible for you to have 0 to 18. In that case, you change it immediately. Probability of x less than or equal to 18 is equal to 1 minus probability of x greater than 18. Because it's easy for you to do 19 and 20 rather than 0 to 18. So that's just the only additional information I want to add. I'll send you a screenshot of this, like I said, and there are interesting practice questions here. Can just start with number 2, okay? We only have about 4 minutes. We might as well just stop. So I'll send you a screenshot. Okay, before then, let's discuss this. If x is a random variable, or let's say a binomial random variable, that is what this notation means. It means a random variable whose probability distribution follows a binomial probability distribution. So when you see this symbol, you can say, oh, x is a binomial random variable with n trials and probability of success of each trial is p. That's what this means. So the probability mass function for a binomial random variable is, for the distribution of a binomial random variable is this. Show that this is equal to 1. How would you do that? Let's do some shots. I don't want to give you as homework. How do we show that the summation of p of x is equal to 1? A. Yes, anyone? X is equal to 0 to n. Help me, anyone? Let's talk about it for 2 minutes only, quickly. We have shown it with just numbers, right? But now we are not dealing with specific numbers. So how do we show? This is the probability definition, yes? So of course you know that this is p minus 1. No, 1 minus p, sorry. Okay, how do we show that px has a summation of 1 like that? Quickly, please. Substitute. Speak louder, anybody who's speaking. Substitute what?
X equals 0.
No. You don't need to substitute x equal to 0. But this is 0 to n. So where do you stop? You don't need x equal to 0. Copy and paste this function in here. This is simply the summation n combination x from 0 to n, right?
Yeah.
P raised to power x, p raised to power n minus x. Which is simply x from 0 to n combination x, p raised to power x, and this is 1 minus. Okay, even if you don't do this, yes, what can you say from here? What is this? This should look familiar.
That's
Come on, come on, come on.
Probability of.
It's not probability now. We are trying to show that it's 1. So what is this in mathematics?